Laplace transform of Clausen function. So in the past few videos, we have been doing a lot about Clausen function, its properties, identities, integral, derivatives, and many more. So now it's on finally for the Laplace transform. We know that Laplace transform of any function is basically defined as um, integral from 0 to infinity of e to the power minus st f of t dt. Yes, this is just the Laplace transform of a function f to the world of s. Now we are doing a similar thing over here, but we know that because the Clausen function of m of theta is defined differently when m is even or m is odd, so we are just considering m is even, and in this case the definition is sum from m belongs to even. Sum from uh, k equals to 1 to infinity of sine k theta by k to the power m d theta. We will just consider this function and then find the Laplace transform. Okay, now let's get back to the work. We know that this is integral from 0 to infinity e to the power minus n theta, and then sum from k equals to 1 to infinity of, this is sine of k theta by k to the power m and then d theta. Okay, now let's take sum outside the integral. Sum from k equals to 1 to infinity integral from 0 to infinity e to the power minus n theta sine of k theta by k to the power m d theta. Yes. Now let's take the constant outside because integral is in terms of theta and k to the power m is just a constant. You can take that out and we are left with integral from 0 to infinity of e to the power minus n theta sine k theta d theta. Now this is just the Laplace transform of sine k theta. Yes, and we know that the Laplace transform of sine ax, Laplace transform of sine ax. Yes, this is just a by s square plus a square, where s is the complex domain variable. Over here, n is that variable. So this will change to sum from k equals to 1 to infinity of 1 by k to the power m, and then over here it will be k by n square plus k square d theta. Now, now this is our final sum that we need to do. Yes, if we make this sum, if we evaluate this sum, we are going to get our answer. Now, the main thing, the main difficult thing will be to evaluate this sum, and let us see how we can make a progress. Sum of given sum n square plus k square. Okay, now over here, how we can make a progress is we would try to want to break this into partial fractions, yeah, but because the m is not known, yeah, so if m is a bigger number, it can, the partial fraction can go up to long forms. So we are just interested in breaking it into partial fractions, and since m is not really a number, it will be difficult to do by the standard means. But yeah, we can proceed in a way where how we can do is we can introduce a similar thing over here in numerator n square plus k square minus k square. This will help reduce the fraction, reduce the denominator into smaller terms, and finally getting to the ones and threes and so on. And since m is an even number, m minus one is odd, then upcoming terms like m minus 3, m minus 5 will also be odd. Now, since I have introduced n square myself, I have to put 1 by n square, I know that, yeah, and then the other cancels out. Now, this is just 1 by n square, sum from k equals to 1 to infinity 1 by k to the power m minus 1. Yes, and then minus 1 by n square, sum from k equals to 1 to infinity Yes, and then the k square and this cancel out, and that gives us k to the power m k to the power 1 by k to the power m minus 3. Yes, and n square plus k square. You can see that this is kind of similar to the previous expression that were initially, just that it had reduced by number 2, and we have 1 by n square over here and negative sign over here. So it can be done in similar way by using similar pattern that we have seen. Okay, so first of all, this is just 1 by n squared times given zeta of m minus 1 here. Now over here, this will just be somehow similar. It will just be 1 by n squared times given zeta of m minus 3, yeah, this number. And again, minus sign, 1 by n squared, and the same thing. 1 by n squared times given zeta of m minus 3 minus 1 by n squared, and then over here, sum from k equals to 1 to infinity. This number will reduce by factor of 2. I mean, not factor, by a number 2. So, k to the power m minus 5 and then n square plus k square. You get this? Okay, nice. Nice. Okay. And then this will now be Riemann zeta of m minus 1 by n square, and this is Riemann zeta of, and this is minus of Riemann zeta of m minus 3 by n to the power 4. Again, this will be plus 1 by n to the power 4 by sum from n equals, sorry, k equals to 1 to infinity, 1 by k to the power m minus 5 by n square plus k. So you can clearly see that this power is decreasing by 2, 2, 2, 2, 2, and eventually it will reach to, because m is even, it will reach to 1. So k times n square plus k square will be there. And once it is that point, we'll try to evaluate that sum, which will be easily evaluatable using the diagonal function. Yeah, we have to reach that point first. Next, let me show you one, by expanding one more term. Riemann zeta of m minus 1 by n square minus Riemann zeta of m minus 3 by n to the power 4 plus, now this will be Riemann zeta of m minus 5 by n to the power 6, and minus, notice that these terms have same expression, so over here also I will have n to the power 6, and then sum from k equals to 1 to infinity, 1 by, now this will be k to the power m minus 7 now, m minus 7 n square plus k square. I hope you are noticing that. Now this will go on and goes on. Let's say if it goes on up to jth term. Let's say if this sum is going up to jth term, what will your expression be? Sum from zeta of m minus 1 by n square minus zeta of m minus 3 by n to the power 4 plus zeta of m minus 5 by n to the power 6 and minus and plus and goes in. Yeah. And our, okay, so our jth term in the sum will be, in the first term we have 1, second term we have 3, third term we have 5. So it's just times 2 minus 1. Yeah. Okay. So that is m minus 2j minus 1. Okay, I got that. Yes. By, now over here just twice the number term. So n to the power 2j. Yes. The sign for odd terms it's plus, even terms it's minus. So sign shall be, sign will be plus 1, sorry, minus 1 to the power j plus 1. Yes, j plus 1 or j minus 1, whatever you want, right? That's completely fine. J minus 1 also works. Yeah. So over here, for first term it's just minus 1 to the power 0, minus 1 to the power 1, minus 1 to the power 2. Yeah, you can make sense of that. Now, this is our jth term. And now, we also have to write the sum that will come after the jth term. Yes. Okay, yeah, yes, it makes sense, yeah. So, basically, in third term, it's plus. So in this term, it's minus b by j minus 1. Okay, that makes sense. Now the sign alternates. So over here it should be minus 1 to the power j now, is it? Okay, okay. So now this one is j, this is jth term actually, what we have to see, this is jth term. Now this one is j plus 1 term. So this should just be minus 1 to the power j. Yes? Yeah, is it? Let me make sense of it. Let me make sense of it first. Okay, does it make sense? Yes, it makes sense. Makes sense. If and yeah, it makes sense. If I write over here j plus one, it will just be j plus two. Yeah, that also makes sense. Basically, the parity of j and j plus two is the same, so it doesn't matter. Okay, now and now we have over here. What do we have next? The term over here in denominator were same. So over here also we will have n to the power 2j. Yes, the sum goes from k equals to 1 to infinity. Now over here, if it was m, is minus 5, over here it's minus 7. So, yeah. So I guess that's slightly different, and we should have 2j minus 3. Is it? Okay, so over here, we had 5, and we had the number increasing by 2. So over here, we have 2j minus 1, 2 to 8 plus 2 to 8, and that gives us 2j plus 1. Yeah, that makes sense now. 1 by k to the power m minus 2j plus 1 and n square plus a square. Now it makes sense. Now it makes sense. Okay, so we have this. And now what I had said earlier is we want this thing, this over here, the numbers in the form m minus 7, m minus 5, they will eventually go to 1. Yeah, because m is even and the subtract odd numbers, eventually that go to 1. So, so we want that this last number be just 1. Yes, so what we actually want is m minus 2j plus 1 to be 1. Is it? Yes. And for that we have m minus 2j minus 1 will be 1, and that means m minus 2j will be 2, m minus 2 will be 2j, and that means j should be m by 2 minus 1. Yes. So this actually finds for us the value of j, for which this term becomes k to the power 1 times n square plus k square. So we have got the value of j, we can substitute over here, and this will be zeta of m minus 1 by n square minus zeta of m minus 3 by n to the power 4 plus zeta of m minus 5 by n to the power 6, and it goes on plus. Now we know that j is just my m by 2 minus 1. So this will be minus 1 to the power m by 2. And over here it will be zeta of. Now if I substitute j as m by 2 minus 1, here it will be m by 2, and to cancel out m minus 1 minus 1. So that's m minus 2. We get zeta of 2 over here. Yes? Or is it not? So let me cross check once again. So if I substitute j equals to m by 2 minus 1 over here, m minus 2 times m by 2 minus 1. Oh, yeah, okay, it's slightly different. It's slightly different. So we get m minus 2 minus 1. That's m minus m plus 3. That's 3. So it was not making sense because there should be odd number, because even minus odd is eventually odd. So I had to cross check it. And so we found the slight error that we have made, and that makes sense now. Okay, and now we over here we have n to the power j is m by 2 minus 1, so that's actually just m minus 2. Yes, yeah. And let's write out last term now. Last term is plus minus 1 to the power j is just m by 2 minus 1, so this will be m by 2 plus 1. Yeah, you guys also remember that this is just the base term. Yeah, this term, and that will be helpful later on. We will need this, yeah. Now there's the this minus one term, so this plus one terms, which is now 1 by n to the power. The j is m by 2 minus 1. So this is just m minus 2, yeah. And sum goes from k equals to 1 to infinity. Again, this is just 1 now, so 1 by k times n square plus k square. Yes. Now we are very close to finding the answer. Just that we don't know the last sum again. We need to find the last sum, except that others can be evaluated easily. Now we can write concisely all the terms in the following notation. Sum from, let's say, I equals to 1, or let's say, what we can do is, this is the jth term, yeah? So we can begin the sum from k equals to 1 to j. Write this as sum of. Now this is how was this sum written previously? Let me see. Okay, so the sign convention was, if we have to look at our previous answer over here, it is just minus 1 to the power k plus 1, yes, and then zeta of m minus 2j minus k, yeah, and then by over here it's n to the power 2j, n to the power 2k, sorry, n to the power 2k, and yeah, that's how the sum is written. And over here, the final value j is just m by 2 minus 1. So this is our sum, yes. And now the last thing, that the last part we need to evaluate, and this will close up our solution. Yeah, and to the power m minus 2, sum from k equals to 1 to infinity, 1 by k times n square plus k square. Okay, so over here, all of these things can be evaluated because this is just in terms of, okay, this is, okay, over here is 2k minus 1. Okay, and there's slight number here, 2k minus 1. Okay, now all of this can be evaluated because we know m is given in the question, and k just goes from 1 to j, and j is just m by 2 minus 1. So all of this can actually be evaluated. Yes, and now this is also just some numbers. Now we need to find this sum. After we get this sum, we will end up with this. We will close the problem. Now to solve this is kind of an interesting sum because it involves uh, polylogarithm. I mean polygon function or diagonal function. Yes. Now how I begin solving this is we have to factorize the n square plus k square as always that we have done. So if we factorize n square plus k square, we need to use complex numbers. And we will pick k as the main number and introduce I over here because the counter is in terms of k. So this will be k plus ni, k minus ni. Yes. And after this, we can factorize it. We can break into partial fractions. Sum from k equals to 1 to infinity, 1 by k. Now this will just be 1 by k minus ni minus 1 by k plus ni. Yes. And we know that we have to take 1 by 2 and over here, that is because that comes numerator when we add these terms. Yes. Now we have 1 by 2 and outside, and we have sum from k equals to 1 to infinity, 1 by k times k minus ni minus 1 by k plus ni. Is it? Yes. Now again, if you have to break the partial fraction, 1 by 2 ni, sum from k equals to 1 to infinity, I can break this into 1 by k minus ni minus 1 by k, and this one is, oh yes, we don't miss the k over here, that comes from over here. Okay, now this is 1 by k minus 1 by k plus ni. Again, we have seen that we need to introduce the 1 by 2 ni over here, the similar reason that I told earlier. Yes. Now, there's something to notice that over here we have 4n squared times minus 1, yeah, which can be taken inside. If we take the minus 1 inside, what we have is over here 1 by k minus 1 by k minus ni, and over here the minus is plus, so 1 by k minus 1 by k plus ni. Yes. And now using the definition of digamma function, we know that digamma of 1 plus a, that is just minus or Masonic constant plus sum from k equals to 1 to infinity 1 by k minus 1 by k plus a. So the definition, using this definition, we can see that we can over here we can say that the sum will be 1 by 4n square. Yes, and then this will just be minus or Masonic constant plus digamma of here's minus ni in place of a, so 1 minus ni, and over here again this is also minus or Masonic constant. Okay, no. If it goes to other side, it will be plus. So this will be plus or Masonic constant plus or Masonic constant because we are finding sum and this goes to other side, so it becomes plus n. And then digamma of 1 plus ni. Yes. Now this is 1 by 4n square 2 times solar Masonic constant plus digamma of 1 minus ni plus digamma of 1 plus ni. Yes. Now we also know that digamma of a plus ib, its whole conjugate, is just the conjugate of digamma of a plus ib, and this is digamma of a minus ib. Yes. Using this property of digamma, we can see that these are the conjugates of each other. So we can write this as 1 by 4n square 2 times Euler Masonic constant plus. Now we know that a number plus conjugate is just 2 times real part of the number. So let's take the other one, diagram of 1 plus ni, and yeah, this seems to be our solution for the sum. Euler Masonic constant plus 2 to cancels out. Euler Masonic constant plus the real part of digamma of 1 plus ni, because n is known, it can be found out by over here it's 2n square. Yes. Now this is the result of the sum that we have been seeking for. Now finally replacing this value in our initial sum, that's over here. If we place this value over here, we get our final answer. Yes. The sum from z equals to 1 to m by 2 minus 1, m by 2 minus 1 minus 1 to the power j plus 1 remains it of m minus 2j minus 1 by n to the power 2j, then plus minus 1 to the power m by 2 plus 1 by n to the power sorry by n to the power m minus 2. Yes, and our sum that we have got is it's just Euler Masonic constant plus real part of diagram of 1 plus ni by 2n square. So this is now Euler Masonic constant plus real part of diagram of 1 plus ni by 2n square. Now this is our final answer. And in the final answer, you can see that we can make a slight modification. That is, use n squared to cancel the n to the power minus 2 and place the 2 over here. Write it as 2n to the power m. Write it as 2, sorry, 2n to the power m. And that's finally the big monstrous answer of the Laplace transform of Clausen integral, where am is even. Let me just give a final check and then make sure everything is going correct. And if it's wrong, I have to remake the video, but I hope it's not. I hope it's not. It seems to be slightly off by a factor of two. But here, let me just search why that happened. Let's just search why that happened. Oh, I got the reason. Over here, it's just ni and ni over here, not two ni that are written over here. Let me just erase this two and make this 2n square, and again make this 2n square, and also continue that, and over here is also 2n square, and 2 cancels out. So that's how I was off by a factor of 2, and now it all seems to be correct, and I can erase this 2 finally. Now if I check the answer, there's really not any mistake, everything is going correct and good, and yeah, this is the answer. So this was the answer, and till the date, it's the weirdest Laplace transform I have come across till now, and I think it's the same for you as well. But yeah, the solution development, it was quite a fascinating journey, yeah, going from anything to everything. So let me just recap what we did in the solution, yeah, and we will finally close the solution. So this is the answer. I'm just placing it besides the question. Yeah, you can see it. Now, the solution development, first of all, we just use its definition and use the Laplace transform of sign, and then we got a weird sum. That sum was actually the cause of all this trouble because we had to use the partial fractions. We had to do it in a lot of ways, and the sum grew on. We had to write this in summation notation, and then we again get another sum. Another sum, we again had to go to the diagonal function and use the partial fractions again and again. We got a factor of 2ni, yes, and we got a factor of 2ni and ni, which became 2n square, and the lap again, the partial fraction over here could be solved using the diagonal functions, and over here we got diagram of a plus ib and a minus ib, which are the conjugates of each other. So we use the real part function and 2 plus 2 Euler-Masonic constant plus 2 times real part diagram 1 plus n. Again, we had a factor of 2 to be cancelled out, and we finally got that amazing sum. And placing it in the original sum, we finally got the answer. So that is how we solve this problem. Hope you enjoyed the solution. Thanks for watching and look forward to seeing you in the upcoming videos too.